Hi, welcome back to Kin 3030 Online. Today we're going to look at the resistance to angular motion, or more specifically, moment of inertia. We're going to review that the relationships between linear and angular motion and the similarities between linear and angular versions of Newton's laws. Most importantly, I think, for this lecture is learn what the moment of inertia is and how you calculate it. So, this might be a typical problem. Calculate the moment of inertia of a thigh with respect to the hip for two individuals, both 60 kilograms, one being 1.6 meters tall and one being 1.8 meters tall, and there's some information there that we will understand by the end of this lecture, so we're going to come back to this at the end of the lecture. So, remembering, of course, that linear motion or translational motion is where all parts of the object move the same. So we can either do this, or it can even be curvilinear, but every point on this object moves through the same distance. Whereas we have the angular motion, where different parts on the object, of course, move different distances, that being farther away from the axis of rotation here is moving farther than the stuff right here, but they all move through the same angle. If we swing something, we also remember that when we let it go, it will continue on in a straight path, tangent to where it was when we let go, because there's nothing anymore to hold it in place at the axis of rotation. So we have linear units of meters per second squared, and we have the angular equivalents of radians per second, and radians per second squared. You'll note that I've got all of the angular measures here in radians, because for the kinds of calculations that we're going to be doing now, which is where we're actually putting an angular measure into, for example, Newton's second law, this is a situation where your angular measure has to be in radians. When we talked about angular measures, and we talked about the fact they could be degrees or radians or revolutions, there were certain times when it actually had to be radians. And the types of things we're talking about today, we really want our angular measures to be in radians. We, of course, can flip back and forth between linear and angular, which we talked about. This is just a very quick review of what we did several lectures ago, with the idea that the linear velocity equals the radius out from the axis of rotation, that distance, times the angular velocity. And of course, just a quick reminder there of how to convert from degrees to radians and back. So, Newton's laws, which we learned in a linear sense, where a body, the first law, where a body will maintain constant motion, which is constant velocity, unless acted upon by an external force, okay, in order to have an acceleration. The angular version, very similar. A rotating body will maintain a state of constant rotation unless acted upon by an external torque. So it's force in the linear version, it's torque in the angular version. which means there is the equivalent Newton's second law, and in that, for an angular version, remember sum of forces equals mass times acceleration. Sum of torques equals I alpha. So what are those? I is moment of inertia, and so it's the resistance, it's the equivalent in rotational world that mass is in the linear world. It's what resists angular motion. In the same way mass resists angular or linear acceleration, moment of inertia, I, resists angular acceleration, because the sum of the torques equals I alpha, and alpha, of course, is angular acceleration, and that angular acceleration has to be in radians per second squared. And similar to linear, we also have the third law, which is for every torque, there is an equal and opposite torque. Okay, so if you, for example, and we've seen it, I've already hinted in it in some of our earlier lectures, that if I have a torque being created by a muscle on, say, the forearm, there's an equal and opposite torque being created by the muscle on the upper arm, right? Which is why they'll cancel each other out, and that's why we have to cut through the joints in order to do those joint equilibrium types of analysis that we did in the last class, or 2 classes ago. So just as we had the kinematic quantities that in comparison of the linear and angular, which were a pure review, we also have a kinetic quantities that can be linear and angular, and the parallel quantities for angular, again, mass is that resistance to angular or to linear acceleration, and moment of inertia is the resistance to angular acceleration. Force is what causes linear motion. Torque is what causes angular motion. We have momentum and angular momentum, which we're going to come back to in a couple lectures. And impulse and angular impulse, they're related to momentum. So, inertia is the body's tendency to resist acceleration. And the greater the mass of a body, the greater the resistance to linear acceleration. The greater the mass of an object, the greater the resistance to angular acceleration also. However, it's not just the mass. It is the mass and the distribution of the mass relative to the axis of rotation that is important. So there's two in linear motion, there's only that one element, mass. But in angular motion, there's this 2 elements to that resistance to angular acceleration, the mass and the distribution of the mass relative to the axis of rotation. So, and you can see that we have so again, it's not just how heavy this bat is, but where the mass of this bat is with respect to the axis of rotation, depending on what I'm rotating it around. The more close the mass is to the axis of rotation, the easier it is to initiate or stop rotation. The farther it is from the axis of rotation, the harder it is to initiate or stop angular motion. So if I'm holding it here, and you can see most of the mass is down at the far end of the bat, it's going to be harder for me to get it started or to stop it. Whereas if I hold it up in the middle here, or even hold it from this end where most of the mass is, it's easier to get it started and stopped. So again, if I hold on to my bat, if I hold on to it here, it's harder to swing. If I hold on to here, it's easier to swing because more of the mass is close to the axis of rotation when I'm holding it here. If you don't believe me, go and grab a bat or some object that has more mass at one end and try rotating it. So, moment of inertia is the property that allows us to describe that resistance to angular acceleration. It includes in it both the mass, because a heavier bat would also be harder to swing, and how far the mass is distributed within the object with respect to the axis of rotation. So, imagine this bat is made up of a whole bunch of little cubes, little particles of mass. A whole bunch of little particles of mass. And each one has a mass m sub I. And each particle is a different distance, right? You know, the particles here are that far away from my axis of rotation, whereas the particles that are here are that far away from my axis of rotation, right? So each mass, each little particle of mass, let's say that each particle is the same. They don't have to be, but let's say they are. But they all have their own distance from the axis that I'm rotating it around. The moment of inertia, or resistance to angular acceleration, that each particle of mass creates to rotation is that mass times the distance of the mass from the axis of rotation squared. So mass of the particle times the r, which is the distance from the axis of rotation, squared. That's for each particle. If I want to look at the moment of inertia of the whole bat, I literally need to add up all of the moments of inertia of each of those particles. So I'm going to, however many particles this bat was made into, I figure out the moment of inertia of each one of those particles, which is the mass times its individual radius squared, and I add each of those moments of inertia for each of the particle together. And that's going to be the total moment of inertia of the bat, for the resistance for me to try and rotate this bat, to try and accelerate the bat, really, around a particular axis of rotation. If I change my axis of rotation, so let's say I was holding it there, then I'm changing my axis of rotation, then I would have to start from scratch because each particle would now be a different distance from my axis of rotation. So it's from whatever axis of rotation you're looking at. So the sum of the masses of the particles times the individual radiuses of distances from the axis of rotation squared. Well, obviously we can't take every object and break it up into a whole bunch of little particles, but there are some analytical approaches that have been created that allow us to figure out what the moment of inertia is. And turns out that when you have the sum of the masses, well, the sum of the masses is the mass of the whole object. So the moment of inertia equals the mass of the object times something called k squared, where k is called the radius of gyration. And k is the distance from the axis of rotation to a point on this. If I took all of the mass and centered it in one location, it would have the same resistance to angular acceleration that the adding up all of the individual squared little particles would. Okay, so instead of adding up all of the individual particles, I instead create a point on this bat where it would be, and I just concentrated all the mass there, and whatever distance it is from the axis of rotation to that point right there, I would call that the radius of gyration, and it would have, if I did that, it would still feel the same to swing, okay? In order to accelerate, it would feel the same around that axis. So we call that the radius of gyration. Note, and this is important, this is not the center of gravity. This is not something that you can look at it like when we did center of gravity, where we went, oh, okay, if I balance this bat at a certain point, that's going to be where my center of gravity is for the bat. This is not that location. This is something that you would get by literally rotating the bat and figuring out how much torque it took to rotate, and how much, and having measured the mass of the bat, I can then calculate what the radius of gyration is. Okay, it's again, not something that you can look at and take a tape measure and measure, or balance and measure. It's something that you would actually get from actually looking at the characteristics of the bat to see what happened. It turns out often, if I was looking at an object, the first axis of rotation I would choose would actually be the center of gravity. So that doesn't mean that moment of inertia is center of gravity. It means that it turns out that if you take any object and rotate it around its center of gravity, that is the easiest place to rotate it. Okay, that is the easiest place to rotate it. And again, you would be looking at your K, your radius of gyration, or K would be, half of the mass would be over here, half the mass would be over there, and it would be at the same radius of gyration, and you would have calculated that radius of gyration. And a lot of testing of an object like this would start with figuring out that radius of gyration around the center of gravity, because that is the smallest radius of gyration of any object, is if you are rotating it around the center of gravity. And again, I suggest you pick up an object somewhere in your household, be it a bat, a hockey stick, a broom, and kind of grab it around where the center of gravity is and try and rotate it. Or grab it around the end and try to rotate it. And you can tell that it's much harder at the end because everything is distributed farther away. And even with a bat, of course, it's harder here than it is here. This would be the easiest, this would be, the next, and this would be the hardest of those three locations. You would have the same sort of thing with a hockey stick, depending whether you grabbed it at the blade end or the handle end. What it represents is the distribution of the mass. Again, it's a measure in a linear distance measurement, so meters, centimeters, that represents the distribution of the mass from the axis of rotation or around the center of gravity, if we do that sort of base one. Again, you can't measure it by looking at it. It's you look at the characteristics of turning it in order to calculate it. And it's, if you have a body, for example, and you're doing a turn and you're more laid out position, you're going to have a higher moment of inertia. The body is going to have a higher moment of inertia. If you're in a tucked position, it's going to be a lower moment of inertia because the mass is much closer to the center of gravity of the whole body. They are usually previously determined by experiment, and then the values are published for the body into anthropometric tables. We've already seen anthropometric tables when we were looking at the center of gravity. This is another column that we often see in those anthropometric tables, which has the fraction of the segment length, which is the length of the radius of gyration. Okay, doesn't mean that the radius of and there will be in those tables versions of it around the center of gravity of the segment, version of it around the proximal end of the segment, and versions of it around the distal end of the segment. So, just a typical type of question where we are calculating that radius of gyration and some of the effects of mass and radius of, and distribution of mass, how that affects things. Let's just look at it. So if we have an object which has a mass of 100 kilograms and it has an initial radius of gyration of 0.3 meters. So the moment of inertia is going to equal 100 kilograms times 0.3 meters squared, which will give us 9 kilogram meters squared. And that's the units for moment of inertia, which when you think about it, kilogram meters squared times radians per second squared, we'll end up with Newton meters. Work that through so that you do that, and that would be I alpha. So kilogram meters squared. What happens if we double the mass? If we double the mass, that gives us 200 kilograms. We still have 0.3 meter radius of gyration. So we now have a moment of inertia of 200 times 0.3 squared, or 18 kilogram meters squared. What if instead of doubling the mass, we doubled the radius of gyration? So we're back to a mass of 100 kilograms, but now we have a radius of gyration of 0.6 meters. And now I is going to equal 100 times 0.6 squared, or 36 kilogram meters squared. So hopefully you can see that if you double the mass, you double the moment of inertia. If you double the radius of gyration, you quadruple the moment of inertia. So a small change in that radius of gyration can have a large effect on the moment of inertia of a body. So the moment of inertia of the whole body depends on the moment of inertia of each of the segments around a specific axis of rotation. And so for the example of a rotation of a leg around the hip, the moment of inertia of the leg will include the effect of the individual moments of inertia of the foot, calf, and thigh with respect to the hip. if you look at this kind of situation, you can see the distance from the center of gravity of each of, so you have a portion that is the rotation of each segment around its own center of gravity, and then you have a portion that is the radius of the rotation of that segment around the hip. So it's the distance from the center of gravity of each of those individual segments to the hip. And if you look at this, you can see that the radius of gyration for that distance from the hip to the center of gravity of each of those individual segments of your leg are much bigger for the situation where you're swinging through this way as opposed to swinging through this way. So clearly, if you're swinging through in a tucked situation, you wouldn't need to use as much muscle torque at the hip because to get the same acceleration, right? Torque equals I alpha. If the torque is being created by your flexor muscles at your hip, and the I is smaller, which it will be when it's tucked than when it's straight, the acceleration, you get more acceleration for the same torque because the that moment of inertia is smaller. So I depends, as I said, when you think about it here, it's going to depend on the direction of the axis of rotation. So clearly, if I'm rotating around an axis here, it's going to have a much, or even around the center of gravity here, the distribution is going to be much greater than if the axis goes down the end of the bat and you're spinning this way. I mean, that if that axis is goes in that direction, you can think at the maximum any particle of mass is only that far away from the axis of rotation, whereas if I'm spinning it around this axis, it's that far away from the axis of rotation. So clearly the direction of the axis is going to have an effect, and you can think of that in body parts. So if I'm doing pronation supination versus doing flexion extension, you can see there's going to be much greater moment of inertia in that. The next one is going to be the location of that axis of rotation, and as we talked about, if my axis of rotation is at the center of gravity, it's going to be the smallest, but if it's going to be at the end of the segment, it's going to increase. Problem, which is that we had two people that have the actually want to look at the moment of inertia of the thigh with respect to the hip, and we have the radius of gyration is 0.4, and this is of the thigh. It's 0.4 times the segment length. 0.54, I apologize, 0.54 times the segment length. Okay, very similar into how we did it with the center of gravity, only this is not something that you could have actually tried to figure out on your own. The mass of the thigh is 10.5% of the total body mass, and a length of a thigh is 0.232 or 23.2% of your total body height. And so for person A, who is 1.6 meters tall, they're going to have a radius of gyration of 0.54 times 0.232. So 0.232 times 1.6 is going to be the segment length of the thigh, and times 0.54 is going to tell you for that segment length how long is the radius of gyration, which then ends up with 0.2 meters. The mass is a 60 kilogram person times 0.105 or 10.5% of the body mass, or 6.3 kilograms, where you can see that the 6.3 times 0.2 squared is going to be your moment of inertia, or 0.25 kilogram meters squared. If we take the same person and same mass but different height, and they're taller, so their thigh segment length now is 0.232 times 1.8 meters, and then times 0.54 gives you the radius of gyration. So now you have a radius of gyration length of 0.226 meters. So we now have 6.3 times 0.226, or 0.23 rounded off, squared, or 0.32 kilogram meters squared. And you can see that obviously the taller person has a larger radius or moment of inertia, because they have a larger radius of gyration, and that has a large effect on the moment of inertia because it's squared. The taller person is going to find it harder to rotate. Well, think about some of the implications of that. Particularly in sports like gymnastics. I've known people who have worked in the gymnastics world and have been a little frustrated because young kids were actually taken out of the competitive stream because of how tall their parents are. Yes, they want to start training them early, but if both parents are tall, then the moment of inertia required to spin and do, like a layout, particularly somersault in a layout position, is going to be quite high for the taller person than for the shorter person. And so somebody who is shorter is going to have quite an advantage in that type of sport, where there's a lot of where moment of inertia is important. So that is what moment of inertia is. It is that resistance to angular acceleration, and the difference between it and the resistance to linear acceleration is resistance to linear acceleration is just mass. Resistance to angular acceleration is a combination of mass and the distribution of the mass. How far the mass is from the axis of rotation. And we call the term that we use to describe that distribution is the radius of gyration.